Hello everyone. We are going to pick up where we left off our last lecture on statistics and talk about the normal distribution today. But let's recap what we've already done and some of the key topics that are going to come up again today. What we've covered in the past are measures of center, things like mean, median, and mode. We have covered symmetry of distributions, and skewness as well, and we've covered variation, more specifically the standard deviation. Now, based on the two graphs you see below, looks like I have two data sets that are unrelated. Okay, they look very different. In fact, both of these distributions are normally distributed. The graph on the left, or the red one, is the length of newborn males in the United States. The graph on the right, which is green, you notice it is shorter and fatter curve. That is the average height of a male in the United States. For babies, the mean, right down the middle there, is 20 inches. And the standard deviation is 1 inch. For American males in the United States, the mean is 69, and the standard deviation, 69 inches, and the standard deviation is 3 inches. So this shows you that normal distribution, these graphs don't look alike. One's very tall and skinny, one's a bit shorter and fatter. But they're both normal. They're both normally distributed, because normal distribution only has 3 characteristics we have to follow. If the distribution is symmetric, which we talked about before, it's bell-shaped. This is where you've heard of the bell curve, and then the distribution needs to have a single peak. Both the graph of the newborn height, newborn length, and the adult male height meet those requirements. So we're looking at 2 normally distributed data sets. Okay, now that single peak that we run into is going to do a lot of work for us. It's obviously going to represent the mean because we've labeled it here. It's also going to represent the median and the mode. Okay, we want our value that occurs the most often to be right there with the mean, have them be the same number, and then also that be the median as well. So there's our correspondence of the peak, and then variation in normal distribution is characterized by the standard deviation distribution. Remember, standard deviation we talked about, it's the average spread or average distance from the mean each data point is located. So here is the most general basic graph of the normal distribution. This is a special case called the standard normal distribution, and this happens whenever my mean is 0 and my standard deviation is 1. So you can see my values across the bottom here on my x-axis, and then you can see my height along the y-axis. Now, I want to show you that our data sets are not our data sets. Let's say it differently. I want to show you how the standard deviation and the mean impact the normal distribution. So if I move the mean, so remember that's the peak. If I change the mean of a normal distribution, and what we're using here, we're using Desmos, we're going to use these sliders to help us. I've got normal distribution right here. This is a built-in function because you don't need to see the function that we're working with right now. If you want to, click right here. When you look at it, you'll get a good glimpse at our function. But our function has 2 pieces of information that we need that are going to impact the shape and the location, and that is the mean and the standard deviation. So as I move the mean around, all it does is just move the peak left and right. But as I move the standard deviation, remember, the higher this value is, the more spread out the data is, and then the smaller it is, the closer together the data is. So you can see how the standard deviation has a huge impact on the shape of our curve. It's still normally distributed, it's still bell-shaped, but the standard deviation, the higher that value is, the shorter and fatter this tail is going to be. The smaller the standard deviation, the taller and skinnier our normal distribution is going to be. So when is this going to happen in the real world? When am I going to run into normal distribution? Well, pretty much most measurable human characteristics are fit into this category. Most of those distributions, height, weight, shoe size, are all going to be normally distributed. Quantities that are impacted by many factors are typically normally distributed. So for an example there, IQ score, SAT scores, and then even car prices. If you've not seen Auto Trader's ads, they've kind of gone off TV recently, but their ads show, did I get a good deal? Did I not get a good deal? And then they'll bring up the graph, and it's a normal distribution. It'll show you, here's what people in your area are paying. That's the mean. And then a determination, did you pay too much, too little, and then how much? Did you get a good deal, a great deal, or a bad deal? And the last thing is manufacturing output. And this is, for instance, if you're working at a Coca-Cola plant and you're filling up the cans say 355 milliliters. Well, not every can is going to have exactly 355 milliliters. There's going to be some variation. All right. Same thing with any kind of manufacturing process. Even mechanized is going to have some natural variation. Now, the mechanized is going to have a lot less variation, but there still will be some, because every can that comes off the line at Coke does not have exactly 355 milliliters. Right? Every nail that comes off does not have the same length. And what I mean nails that are all meant to be the same length. If you open it up and measured each one of them, you'll see some variation. It's going to be very small, but there's still variation there. Okay, so I've got some examples of where you may run into normal distribution in the real world. And the first example here is a test done, or a survey done in 1846, where they measured the chest circumference of 5,738 Scottish militiamen. And there is our histogram. So as you look at our histogram, you can see, if I follow this up and come back down, I'm looking at what looks like a normal distribution. Okay, this is one of the first data sets where this was documented and then talked about later. What else works that way? Well, there's your chest size. Or your chest circumference for men? How about weights of all the FIFA World Cup players? Look at this. Isn't that beautiful? Same thing. We got that normal distribution going out there. Now, does it work with every data value of everything? No. Here's the data set that shows the frequency of the numbers of soccer players in the FIFA World Cup. There are 736 players in here. This data is not normally distributed. This data has a uniform distribution. And the reason for that is there is no value that everybody gets, or there's no number that everybody wants, and then more people want the numbers directly around that. So if your favorite player has number 7, you may want to get number 7, but you could get any number on the available to you. Also, the soccer jerseys tend to stop at 25, so that's what's limiting our X values here all the way up to 25. And typically the numbers correspond to a position on the field. So this is a uniform distribution. This was one of my more interesting data sets that I found. This was the age of the first 44 U.S. presidents on the day they were elected. And once again, right, we're looking at a great normal distribution. So yes, this one's normally distributed. How about, now I know there have been 46 presidents, so if I add the next 2, we get a skew to the right. So your data is skewed a bit to the right, and that's because the last 2 presidents have been older. So take a look at where our bar graph ends with 44, and then 45 and 46 lie to the right of that. Because normal distribution does not have a formal definition. It's frustrating. I can't tell you a numerical way to say this is normally distributed, this is not. All the data has to do is follow those 3 rules we laid out. Okay, so even though this one's got a bit of skew to the right, it's okay. It is still normally distributed. And then lastly, I got the weights of 2,764 NFL players and for the 2016 season. This is not normally distributed. In fact, there are two distributions going on here. One of them is one of our peaks here is around 200 pounds, and then one of our peaks is just over 300 pounds. The reason you're going to see something like this in soccer, but not, or something like this in football, but not in soccer, is because there are positions in football where you want your players to weigh a whole lot more. So positions on the line, defense and offense. Whereas if you're a skilled player like a receiver, or running back, or quarterback, you don't want to be too big. So in this case, just because we have data that has something to do with a measurement, that doesn't mean it's going to be normally distributed. So from here out, though, I want to talk about our working with normal distributions. What we're going to do is consider data values that are continuous. And the reason is the graph that gives us our normal distribution is a continuous function. So instead of being able to calculate, here's a data set, how many people are exactly 71 inches tall? I can't do that. That doesn't make sense when I'm dealing with continuous data. And if you want to remember continuous and discrete data, take a look at the lecture previously from this chapter. So how am I going to do it? Well, it turns out in probability, what's going to happen in probability dealing with continuous data that is normally distributed, to find the probability, I'm going to need to calculate the area under the normal curve. It sounds weird, right? It sounds a little odd. So I want you to think about this example. What if I told you that there is a satellite crashing to Earth, and it's definitely going to hit Earth, but we don't know where or when. And I want to find the probability that it hits land. Well, the probability it hits land, I need the total area of the surface of the Earth, and I need the total area of the surface of the Earth covered by land. You have those two numbers here, 54,225,000 square miles covered by land, 196,940,000 square miles covered totally. That's the entire surface of the Earth. If I divide those, I get 0.275, and now I've calculated a probability by using the area. So what's this going to look like for us? So let's consider our data set from above, where I have the heights of American males. And I want to calculate what's the probability if I randomly select an American male, they fall between 66 inches and 71 inches tall. Well, how do I do this? Well, this is what the graph is going to look like. You can see the shaded area. That area is going to be our probability. Okay. So, and we're going to use technology and tables to help us out when it comes to calculating these. These are things, not things we're going to want to calculate by hand. Now, over to the left, this is that normal distribution. I have find cumulative probability. This is how we're going to find our area. So as I move these numbers around, my area is going to change sizes. So the difference, or the amount of area, is going to change. So let's get back and show you why this is so cool. So normal distributions. Instead of having to carry around big data sets, now if I can get three pieces of information, the normal distribution density function, normal distribution function, which we're going to be using technology for, so don't worry about that, the mean of the data set, and the standard deviation of the data set. If you give me those three things, I can give you a graph that's a normal distribution. That means I can carry this around in my pocket and do interesting things with the data. Finishing up, we know so much about the normal distribution that it turns out for any normal distribution, 68% of our data is going to fall within one standard deviation of the mean, 95% within two, and 99.7% within three standard deviations. We'll talk more about this tomorrow. And so if you have any questions, shoot me an email. I'm happy to talk about it. And then we'll finish up these notes on our next recording.